Hey everyone, I am going to talk a little bit about section 1.2, which is a section about matrices in our textbook and our course. As you see, I've pulled up the linear algebra guided notes, and I'm going to be writing right on top of these to give a little bit more context for these. All right, so we talked about linear systems a little bit, and I fixed some typos that I found in this section, but we can scroll past those. And I want to talk about matrices. So the first thing that we see here is an m by n matrix, which we tend to write with a capital letter A. It's an array. It has m rows and n columns. And oops, here's another typo. The entries are, in our course, most of the time they're real numbers. Occasionally you'll see that they're maybe complex numbers, or maybe there are other number systems out there that you'll learn about in modern algebra and real analysis, and we can make matrices with entries from those systems. But in this class, you can assume, unless we've said otherwise, that these are real numbers sitting in this matrix. And we'll often write this in short form as just brackets Aij. And the way to say that this is an m by n matrix is to write this little E symbol. So that's the mathematical way of writing in. And if you're using LaTeX and you just wanted that symbol, that would be $signs for math mode. And then in would be the way that you get that little E. But we want to write more than that. We want to write this is in. And then we'd say M. And we use subscripts here. So use subscripts, and we've got M times n. So it's in the set of m by n matrices. And that will produce something that looks like this little E symbol, this in symbol, and then a subscript m times n, which you see again right there. And that tells us the dimensions of the matrix that we're looking at, which is important because I could have, a 3 by 4 matrix or a 2 by 1 matrix, and they're different, they have different sizes. There are some special cases with matrices. So I don't know, let's write down a matrix. So I could write down 1, 2, 3. I'm very creative. You can see 4, 5, 20, right? So that is a matrix. It has 2 rows and 3 columns, right? Our rows go horizontally and our columns go vertically. And I said it had 2 rows. So let me get rid of one of those. So I've got 2 rows. And I've got 3 columns. That's what this 2 by 3 tells me. 2 rows, 3 columns, and 6 total entries. If I have the same number of rows and columns, we call the matrix square. So if I had written instead 1, 2, 4, 5, this is a square matrix, and you see why we call it that. It sort of looks square, right? We've got the same number of rows and columns, and when we actually write it out, it kind of looks like a square shape. There are some pieces of this matrix, or there's a particular set of entries that we're interested in. They're the ones that sit on this thing called the main diagonal. The main diagonal goes from the top left to the bottom right. And so the diagonal of this matrix is going to be A11, which is 1, and A22, which is 5, right? So those are the entries on the main diagonal of this matrix. And we're going to talk about something that we do with the entries of the main diagonal. We get something called the trace of a matrix. So you could do the trace of the matrix 1, 2, 4, 5, which is the sum of the entries on that main diagonal. So we do A11 plus A22, that's 1 plus 5. And if I haven't been really, under caffeinated today, that should come out to be 6. So we use the trace to tell us something about the matrix. We'll talk more about how we use trace later. We could also, if we wanted to, talk about other special entries of a matrix. We could talk about the entries in the ith row. And so here you see I use the notation row I sub A, row sub I of A to pull out the ith row. And in here, right, here's my ith row. Whoop. Pull that guy out, and I write him as a little 1 by n matrix. I have 1 row and n columns. So that's the ith row. I could also pull out the jth column if I wanted to, and that is that blue column up there, right? And I write this as an M by 1 matrix. It has M rows and 1 column. So that's that guy. And so we can isolate entries of a matrix. We can isolate the rows of a matrix, the columns of a matrix. If we have a square matrix, we could talk about the main diagonal. And if we're writing down matrices and we want to pull out a single entry, we could do it by saying something like A1, 2. And in this matrix up above, that just gives me, you know, little A1, 2. Our convention is usually to say, like, if we have capital A, its entries are going to be lowercase a, but we still want to tell our reader that. But if I call this matrix that I started with up here, which I'll write in blue, let's call that matrix B. If I look at B, let's say second row, second column, B22 is 5, right? So that's a way of pulling out an entry. And we'll see why that's useful. We're going to have some matrices that we build from other matrices, and it's sort of nice to be able to just slap some brackets on there and talk about which entry we want. So we can pull out, let's do this in a different color. We can pull out entries of a matrix with some brackets, right? We want the ijth entry. We could pull out a row. We do row I of A, or a column with column J of A. Or if we have a square matrix, we could pull out the diagonal, which you could list as a set, A11, A22, up to ANN. And we know we're going to have an ANN, and that should be the last entry in our matrix because it's square. N and M are equal. So that's some notation and some things we can do with matrices. If I refer to something as a vector in this class, so this is down here, if I call something an M vector, what I mean is that I'm talking about a column vector that has M entries in it. So it has height M. Unless I specifically say like row vector, if I just use the word vector, I'm probably talking about a column vector. That's sort of the default choice in this class. So an M vector means a column vector with M entries in it. So it's 1 column wide and M rows deep. All right, so that's some background here. I want to give you a writing tip for when you're writing about matrices in LaTeX. If I give you a matrix A, I say, all right, this is just some matrix A. It's an M by N matrix. If I don't want to use the bracket notation, right? So if I'm trying to write something like, you know, the ijth entry of A, and I just write down Aij, I need to tell my reader that Aij means the ijth entry of the matrix A. So I might say something like, in this italicized text here, given A and M by N, let Aij denote the ijth entry where 1 is less than or equal to I is less than or equal to M. So I is telling me how many rows I have. And 1 is less than or equal to J is less than or equal to, oops, that's an N, right? And J is telling me how many columns I have. Or if you want to be really concise, you can say, let A equal brackets Aij in M N by N. And this is very concise. The LaTeX for this thing, I have the word let out front, and then I have A equals bracket A sub curly braces Ij, and my curly brace and my bracket, the little in symbol, and then M underscore curly braces M times N. N dollar signs, which is the end of this thing called math mode. Math mode is how you write math in LaTeX. And the easiest way to do it, and let me move this dollar sign. I erased too much. There we go. Is in between dollar signs. But you're going to be pros at this soon. This is just as a reference if you want to come back and see how to type something like this up. What this very concise line of text does is say, okay, A is this matrix, it has entries Aij, and I know the size of the matrix because I've said it's in the set M by N, and that tells me that I goes between 1 and M, and J goes between 1 and N. And this also announces to your reader that lowercase a with some subscripts is talking about the ijth entry of the matrix A. You can skip that if you're okay with using the brackets. It's the same as saying, like, you know, brackets Aij, but it's a little clunky. I mean, the lowercase letters are nice to read. All right, so if I take this matrix in example 1.3, I've given it some letters A, B, C, D, E, and F. Those are all real numbers. Some questions we might ask are, how many rows? How many columns? Is it square? How many entries does it have? I think those are probably all the questions we would ask at this point, but let's just practice a couple things. So I see that it has 2 rows. It has row 1 of A is the row ABC, and row 2 of A is the row DEF. As for columns, I see I've got column 1, column 2, and column 3 of A. Column 1 is AD, column 2 is BE, and column 3 is CF. It's not square. Nope, because I have 2 rows and 3 columns, and to be squared, I need the same number of rows and columns. M is not equal to N. And finally, if I wanted to pull out an entry, like let's say that I wanted to pull out the 1, 3 entry, I would look in the first row, the third column, and I'd get the real number C there. So that's how we work with our matrices. How many entries does it have? It has 6 total. And it has M times N entries. Okay, so that's just a little example to kind of help you navigate your way around a matrix. We could talk about rows and columns. We could talk about entries. We could identify whether or not it's square. Now that we have the idea of a matrix, we want to figure out what can we do with them? Can we do operations on these things, right? As I said on the first day, the algebra part of linear algebra is the talk about operations and what properties do they have. So for instance, we probably want to figure out, how do we know if 2 matrices are equal to one another? And then if we know that, we could start talking about, how do we add them? How do we subtract them? How do we multiply them or scale them or do all sorts of operations? So I've left this definition blank here because I want to talk through what it might mean for matrices to be equal and give you a sense of how mathematical definitions come about. So one thing to think about is, you know, what are some things that aren't equal? So if I write down, so here's some scratch work on the side here. If I write down the matrix 1, 2, 3, 4, and the matrix 1, 0, 2, 3, 0, 4, I might ask, are these matrices equal? And I'll put quotations around equal here with a little question mark underneath it. Like, yeah, they're kind of similar, right? They only have 1, 2, 3s, and 4s in them, aside from some zeros, but it seems kind of weird to say 2 matrices of different sizes are equal to one another. So probably this isn't very useful, so probably not. We're probably going to insist that our matrices have the same size. So already I kind of want to start editing the definition of matrix equality. I might say here 2 M by N matrices A and B, so that both A and B have the same size, right? So both A and B are M by N matrices. So this is forcing them to be the same size. Okay, so we ruled out this case. We probably don't want different size matrices to be equal. What if I write down 1, 2, 3, 4, and 4, 3, 2, 1? These matrices look similar. They've got all the same numbers in them, just rotated around a little bit, but probably I don't want them to be equal. Again, probably not. Because I have this intuition that says if these things are going to be equal, it's most useful if like this top left entry over here is the same as the top left entry over here. I probably want those to match. So what I want to say is that these are equal if, I'll use the bracket notation, Aij equals bracket Bij for all I between 1 and m, and j between 1 and n, right? So they have the same entries in the same position. And if I had just written that definition out, you probably wouldn't have really blinked. You would have been like, yeah, that makes sense. But I just wanted to point out that when we write down mathematical definitions, somewhere someone has made a choice about what does equality mean? What does addition mean? What does it mean to say that these two matrices are actually the same? And so what it means for us is the matrices are the same size. And if I look in a position in each matrix, I should find the same entry. So two m by n matrices A and B are equal if the ijth entry of A is the ijth entry of B for all I and j in the appropriate ranges. Okay, now that we've gotten matrix equality ironed out, we can start defining what we mean by matrix addition or scalar multiplication. So our next definition is matrix addition. If I have a matrix A with entries Aij, and a matrix B with entries Bij, and they're both m by n matrices, then the sum is the matrix with entries Cij, where the ijth entry of C is just take the ijth entries of A and B and add them together. And again, I've got this typo. I'll fix that typo. Whoops, that should have been in LaTeX. That should have been an LEQ for less than or equal to. And we probably don't want to like write down a matrix C and say the ijth entry of C is the sum of the ijth entries of A and B. We'll probably just instead describe the matrix as the matrix A plus B. So here, A plus B is the name of a matrix. A plus B is a new m by n matrix where, if I wanted to use the brackets, I could say A plus B ij is really just the ijth entry of A plus the ijth entry of B. And you've probably even added matrices before and done it this way because it's the totally sensible way to do things. But what it means for two matrices to be equal is that we should be able to compare the ijth entries and get the same thing. And so this is really saying on the left, the matrix A plus B, I've told you exactly what its ijth entry should be. That's what we mean by equality. So here's an example. If I take A and B as an example 1.4, then in order to get my new entries, the top left entry, the 1, 1 entry of the sum A plus B is going to be the top left entry of A, 1, plus the top left entry of B, 2, which apparently I added together and I got 0. Geez, Professor Gibbons, that was not good. This is a 3. Okay, let's check the rest of them, having seen that terrible error. Okay, 1 plus 2 is 3. -2 plus 0 is -2. 3 plus 4 is 7. -1 plus 6 is 5. 2 plus 1 is 3. And 0 plus pi is pi. I don't know where that first 0 came from. Whoops. Anyway, you should always check my arithmetic. There's evidence that as you learn more abstract math, your basic arithmetic neural pathways get written over. So you can just trust that I'm a very good abstract mathematician, but not so hot at the arithmetic. Okay, so we've got this notion of addition of matrices, right? We can just add them by adding up the same entries. And of course, we couldn't do this if they weren't the same size. So most of these definitions are going to have to tell us like something about the size of the matrices that make them compatible. Now, what we see next is this thing called a proposition. And what a proposition is, it's like a little fact. Then this little fact is, if I have an m by n matrix called A and another m by n matrix Z, where every entry of Z is 0, then A plus Z is the same thing as Z plus A, is the same thing as the matrix A. And so we call this the zero matrix, partially because it has all zeros in it, but also because it acts like zero does with, with numbers. Like if I take 2 plus 0 or 0 plus 2, I get 2 back. And this is saying if I take A plus the zero matrix, or the zero matrix plus A, I get A back. So that's the reason that we call it the zero matrix. And anytime you have a little fact like this in mathematics, you're going to have a proof that follows it. And let's think about the pieces, like what we know, what's in our mathematical toolkit so far that we can use to prove this thing. Well, we have 2 definitions that are going to be useful. So here's some thinking on the side here. So useful definitions. We've got the definition of what it means for things to be added together. So the definition of plus. And we want to show that these matrices are equal to something. So we're going to have to use the definition of matrix equality. And these things feel so obvious that it's almost hard to like zoom out to this level of abstraction where you're like, yeah, there's a definition for that, and I'm going to have to refer to it. Anyway, let's imagine what happens when we actually start writing this proof. So we've started the proof. So there's a little sort of call and response in writing proofs here that I'll alert you to. So the first thing I have in my proposition is the statement for all A in M by N. And in the first line of my proof, I echo that. I say, okay, let A be a matrix, be an M by N matrix. And that's to say, all right, I'm in the situation that this proposition applies to. The next thing I have is this if statement. If Z is the matrix where each entry is 0, then something's going to happen. And in my proof, what I do is I say, okay, sure. So if that's the case, let me assume that that's the case. And then finally, I take the rest of my proof. I've got this then statement. It says then blah, 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 blah should happen. And I get a therefore, blah, 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 blah does happen. And then there's a little bit more to this one. I've got a furthermore, and I'll just quickly flip to the next page and then come back. So this furthermore, it gets its own little proof, right? So we're saying furthermore, Z is unique. And so we're going to say, okay, next we've got to show Z is unique. So we're going to do all of that in the proof of this proposition. Okay, so how do we actually do it? All right, well, we've picked our matrix A. We've told our reader what the entries are. We've assumed that Z is the matrix where each entry is 0. So let's consider A plus Z ij, which is equal to the ijth entry of A plus the ijth entry of Z, which is 0, which is Aij, right? This is true for all I between 1 and M and J between 1 and N. And that's what it means for matrices to be equal. So I could say therefore, and probably I want to put right after my therefore, by the definition of matrix equality, A plus Z equals A. And because nothing really exciting is going to happen when we switch A and Z in this, I'm okay if we just say similarly Z plus A is also equal to A, right? We don't need to make this like as formal as a high school geometry proof. But we've used the definition of matrix addition. So maybe let's even put that in here. I'm doing a little bit of editing here. So I'm gonna, oops, the eraser's way too big. Let's fix that. I'm gonna add something in here, and I'm gonna do it in a slightly different blue so you can tell that I'm editing. So by the definition of matrix addition. And when you add matrices in proofs, you're not always going to say by the definition of matrix addition. Right now, we've only got really 2 definitions that we can use, so I'm making sure to let you know where I'm using them. Okay, so we've got that A plus Z and Z plus A are both A. Now I want to show that if there's another matrix that has this property, it actually has to be the same thing as Z. So the way that we do that is we show that if we pick a matrix W that has the same property, so suppose that for all A in the set of m by n matrices, there's a matrix W for which A plus W equals W plus A equals A. Now I want to somehow show that W and Z are the same matrix. What I'm going to use is the fact that Z is a matrix in m by n, which means I can kind of plug in Z for A. And that's what I do here. This means that Z plus W equals W plus Z equals Z. But at the same time, we just proved that Z plus W equals W plus Z equals Z. And therefore, equals W, right? Because Z you can add to anything and you get the other thing back, right? So we can use the property that Z has. And this means that W and Z are the same thing, right? We've got Z plus W is Z, but it's also W, and so Z and W are the same thing. So that's it. That one could be really quick. Or you could do the same thing. You could go with the entries and you could do an entry argument and say, oh, well, this means that the ijth entry of W has to be 0. So it's kind of neat. When you're writing proofs, you can use things that you proved earlier in the proof to show things in your proof. But that means that any matrix I pick that acts like the 0 matrix actually is the 0 matrix that has all zeros in it. And so we just proved our proposition, which is kind of cool. Okay, there are a couple more operations that we have here. We've got scalar multiplication. So I can take a matrix A, multiply it by a scalar R, and get a new matrix. If I look at the example, I took a matrix A, I multiplied it by the scalar R, which is pi. And all I'm doing is taking all of the entries of A and multiplying them by pi. And we should probably double check after I just said 3 was 0 on the last slide. Let's make sure we're good. Well, pi times 1 is pi, and pi times -2 is -2 pi, 3 times pi is 3 pi, and pi times -1 is -pi, and pi times 2 is 2 pi, and pi times 0 is 0. So, okay, yay, I did some calculation correctly. I got this one right. So we can, similarly, if I wanted to say, okay, what's the 1, 2 entry of RA, I can use the brackets to pull that out, and I get -2 pi, right? And I could talk about row 1 of RA, and that would be the matrix pi, -2 pi, 3 pi, or column 1 of RA, which gives me a 2 vector, a height 2 vector, pi, -pi. So I can put, I can do the same thing that I do with matrices to all of these. You just sort of plug them into the rows or columns or whatever. So we can do scalar multiplication, which you know from calculus. You've scaled vectors before. Scaling a matrix, same kind of thing. And once we have sums and scalar multiples, we can do this thing called a linear combination. And we're going to spend some time in class talking about linear combinations. Linear combos are probably like the top most important thing in chapter 1, if not all of linear algebra as a system of thinking about stuff. The idea of a linear combination is you get some matrices that are the same size. So I've got k of these m by n matrices, and I get some scalars. I scale my matrices and add them together to get a new matrix, and when I do that, I get this thing called a linear combination. And let's think about the word linear here, right? The idea of linear is like, I've got these coefficients. So maybe you could think back to our examples where we had like 2x plus -1y equals 6 or whatever it was in our first thing, right? The idea of linear is I've got these coefficients. These are like my c's down there. And I've got matrices. And they're not like powers of matrices. I don't even know what powers of matrices would mean, but I've just got like, one matrix times a thing plus another matrix times a thing. It's like sort of like x times a thing plus y times a thing. And that gives me a linear combination, meaning it's kind of line-ish or plane-ish in the way it's presented. And we can do this with variables too. So let's look at example 1.6. Let's say that I have the matrix A1 is a vector, it's 3, -1, and I have A2 is another vector, -2, 5, and A3 is another vector, it's the vector 1, -1. Then I could take the linear combination x times A1 plus y times A2 plus z times A3, and what I get is a 2-by-1 matrix. It's another vector, although it doesn't quite look like a vector because it's got all of these variables in it. But I get this matrix B, and let me just write it one more time. I get the first vector A1 times x, so I get 3x, oops, typo here, times -x, right, when I scale that guy. And I get -2y, so I get minus 2y and then plus 5y when I multiply A2. And A3, I get plus z minus z, right? It's still a 2-by-1 matrix. It's just that I'm now adding this, like my first entry is this polynomial that looks a lot like a plane, 3x minus 2y plus z. And my second row also looks like a plane. I've got -x plus 5y minus z. Okay, so we're going to do stuff with linear combinations right now, and we'll play with these some more. Transposes are a way of making sense of matrices that it's really just a way of switching rows and columns. So if I take a matrix A and then I take the transpose of A, what I'm doing is saying, oh boy, here I go again with my typos. A is an m by n matrix. So let's pick one. I'm going to borrow a matrix from the numbers I see on the page. Let's say that this is my matrix A. And this is a 2-by-3 matrix. Then A transpose is going to be a 3-by-2 matrix. So here in my definition, I should switch my m and n, and I did half of that. I'm going to have an n times m matrix at the end of the day. And what I do is I switch the indices. So A11 is 3, and A12 is -2, and A13 is 1. And in my transpose matrix, this becomes, so A11 is A transpose. I switch 1 and 1 and I get 1, 1. So I get a 3 there. And A12 is going to be A transpose, but now that's going to be the 2, 1 entry, which means it's the second row first column. So I get a -2. And A13 is going to be the 3, 1 entry of A transpose. So I'm going to get a 1 in the third row first column. And so really what happened was I made that first row into my first column. And that's going to happen with my second row as well. I'm going to get -1, 5, -1 as the second column of A transpose. So with transposes, you can think about switching rows and columns. And if I take A transpose and I transpose it again, you probably won't be too surprised to discover that we get A back, right? Because I switched the rows and columns and then I switched them back. One reason that transposes are useful to us is actually just to write things down. If you look at example 1.6, it's kind of like those big, tall column vectors take a lot of space to write down. But if we write them as row vectors and then put a transpose symbol behind them, they are still column vectors, but they're written horizontally, which is actually kind of a useful trick, just typographically. There are other good reasons to take transposes that we'll see, but probably this is the most immediately useful of them. All right. We are going to talk about matrix multiplication next time. And we're going to talk about matrix multiplication and we're going to tie it into linear combinations. And so you see here, we've got this linear system of equations. So we've seen this before. And we want to rewrite it to actually look sort of line-like. We're going to rewrite it as AX plus B, where A, X, and B are matrices. And so we take A to be the matrix with all the coefficients in it. So it's an m by n matrix, right? Here, this is an m by n matrix. We're going to take X to be the vector of variables. So this is in n by 1. I have n variables, so it's got n entries high. And B is going to be a column vector of height m because I have m entries in it. And that sort of tells me, like, if this AX is actually matrix multiplication, it sort of forces me to define it in a certain way. So we're going to start here and talk about this little linear system and how we're going to rewrite it as a matrix equation and what that means for us in terms of how we have to define matrix multiplication. And then we'll see probably one of the most super useful theorems in the entire course of linear algebra. Like if you've got to like just say by some theorem, you should probably say by this theorem. It's that good. We're going to get into that, and that'll be a way for us to review linear combinations, sums, scalar multiples, what we mean by subtraction, things like that, and how we tie this into solving linear systems of equations. So that's where we're headed. Thank you for your attention. I hope this video was not too long or too scattered. If you have feedback, I would be happy to hear it because these videos are for you. All right, I will see you soon. Stop recording. Stop. All right, there we go.